When we wish to test or estimate means for only one or two populations, we would use either the one or two sample t inferences from earlier. Now, when you want to test for differences in two or more, typically in more than two populations or at several different levels or values of a categorical variable, then you have to take a little bit different approach. This is something we call analysis of variance, or a lot of times this is called ANOVA for short. Every once in a while, if you look like on the internet or something, you may see it as AOV instead of ANOVA, ANOVA. But what ANOVA does is it takes all the variability in the data, all of the sums of squares, and it divides it into two pieces, something called a within treatment variability and a between treatment variability. Now, sometimes we think of different populations that are being compared. Another way to envision a study is to think of the overall characteristic as a factor, and then each different group you're comparing, or each different level, as we call it, of that factor being the things that you're going to compare the means of in terms of the population. For example, we could consider race as an overall factor, and then the levels of race, which might be considered in an analysis to determine if mean height is different among races, could be things like Hispanic, African American, white, Caucasian, and then other races. Let's look at some examples and determine how we might create an objective method to make some of these inferences. So we're going to begin with a situation where I'm looking at students who take Stat 205, and a lot of the majors that are present in Stat 205 include nursing, psychology, middle grades education, and biology. I want to see if the average course grade differs between any of these groups. Now, the four majors are like four levels of a treatment variable, which I might call major. The treatment variable is going to define your different populations of interest. Now, sometimes we can control the treatment variable, such as when you're giving different medications. But other times, you're just observing which category or which level of the treatment variable an observation falls into, such as when we have people self-declaring into majors and then taking a course. The specific ANOVA example we're considering is called the completely randomized design. And the idea here is that the samples for each treatment are independent random samples from larger populations of interest. So you're sort of extending what you would do in the independent samples methods discussed earlier. What we're going to do is examine the amount of variability in the entire data set, specifically dividing it into two pieces or two parts. The within variability is going to try to quantify the variability in course grades within each particular major. So how much do grades vary among nursing students? How much do grades vary among psychology students? How much do grades vary among middle grades education students? And how much do grades vary among biology students? Now, the between variability attempts to quantify the differences between the average course grades for the four majors. So how different are the mean for nursing, mean for psychology, mean for middle grades education, and mean for biology student grades? ANOVA seeks to answer the following question. Are the differences between the four sample means just what we expect from random variation, because not everybody gets the same grade? Are the differences we're seeing in sample means just that random part, or is it something more indicative that there are true differences in performance based on major? So we're going to look at some different scenarios where sometimes it's obvious, sometimes it's not, whether there are differences or not. So suppose in scenario 1 here, the data looked like the following. So for the nursing students, the 5 grades were 81, 82, 83, 84, and 85. Now, if you're very careful in looking at each of the other columns, psychology, education, and biology, you will notice that the numbers 81 to 85 are all there. Just like in the first column, they're just in a different order. So if you calculate the sample mean, if you add up 5 numbers and divide by 5, you're going to get 83 for each of the 4 majors. So the mean for nursing students was 83, the mean for psychology students was 83, the mean for education students is 83, and the mean for biology is 83. So the sample means are all identical, they're equal. Each sample also has the exact same variability because the numbers all go from 81 to 85. Do you think the population means should be considered different if all the sample means are equal and each group, each sample, had the same variability? In this case, you wouldn't think so because all the sample means are the same. There's no reason to believe the population means would be any different from each other. Now look at scenario 2. In this case, it's sort of obvious that some students from majors perform better or worse than others. For example, nursing and education all had scores from 81 to 85. Psychology had scores from 91 to 95, and biology had scores from 71 to 75. In this case, the means are all the tens, digit, and 3, right? So nursing and education had sample means of 83, psychology had a sample mean of 93, and biology had a sample mean of 73. In this case, it's very easy to say psychology students had the highest grades on average, nursing and education students were in the middle, and biology seemed to perform the lowest in terms of the mean scores. Also notice the variability is exactly the same in all 4 samples. It just went from the tens digit 1 to the tens digit 5. So the variability is equal across the samples, but what you're seeing is that the differences between the means, right, 83, 93, 83, 73, is big compared to how the variability is within each major, right? 81 to 85 varies a small amount versus those differences of 10 or 20 in the sample means. So now let's look at a case where it's not so easy to see what's going on. In this case, you have slightly different variability within each major, but also just glancing at the numbers, it's hard to tell where the centers or the sample means are for each of the 4 majors also. In this case, we would really want to have an objective way to put the numbers into some equations and let it spit out results for us. And that's what analysis of variance does. When you're doing the analysis of variance method, what we're doing is called a one-way ANOVA, and the idea is you have k different populations which are all independent, or k levels which identify your different populations, and they're independent. Each population has the same variance, so the variability in each population is the same, so we just write that as sigma squared. Each population has some mean, even though I don't know what it is, right? And we can, in general, write that as mu1, mu2, all the way up to the kth mean. And then each population is either normally distributed, or we want to make sure we have a large enough sample size to believe that the sampling distribution of the mean starts to come into play and everything's going to be okay. Now, we're testing whether all the treatment means are equal or not. So we want to say, hey, are the means different anywhere versus no, they're all the same. So under the null, we're saying all the k different population means are equal. They're all the same number. And then under the alternative, we're saying they're not all the same number. or at least two of the population means are different. Notice that doesn't mean all the means have to be different than all the other population means, but it means there's got to be at least two that are different from each other. The test statistic for ANOVA is called an F statistic. The value of F is just the ratio of variability between your sample means, how different are your Y bar values, and the variability within each sample. How much variation is there within each of your levels, each of your K different groups. Now the F follows what's called an F distribution, and it is indexed, or it depends on two different values. The first one is called a numerator degrees of freedom, and it is just K minus 1. And K is just the number of different populations or groups or levels of your factor being compared. The denominator also is going to depend upon K a little bit, but it's the overall number of data points in the whole study. How many total observations do you have in, minus the K groups. So N is your total study size, and K is the number of groups you have, and that forms the denominator degrees of freedom. StatCrunch is going to call your different populations being compared treatments. The variability between the treatments, or the measure of how different the sample means are from each other, how much variability they exhibit, is called the MS treatment, or mean square treatment value. The within variability, or the variability expected just by chance, just by randomness, is measured by the MS error value, or the mean square for error. Now here the term error doesn't mean mistake, it just means natural differences that occur that are not explained in the model that you're fitting. So F is really the mean square for treatment value divided by the mean square for error. Now let's go back and think about what our samples looked like and what the output would look like from StatCrunch. So this table is called the ANOVA table. Notice it tells you you have a line for treatments and you have a line for error. And what it does is it looks at the total variability, okay, or how different are the sample means. And remember, in the first scenario, all of the scores in each group were 81 to 85, so all the sample means were 83. Well, 83, 83, 83, and 83 exhibit zero variability, so that would be the zero under the SS, and then the mean square would be just the sum of square the SS number divided by the degrees of freedom. Now there were 4 majors, so 4 minus 1 gives you the 3 degrees of freedom for the treatment variable. The mean square is 0, and that's the numerator of your F statistic. Now on the error line, so this is your random component, this just measures how much variability there is within each group. So how much is 81 versus 83, 82 versus 83, 83 versus 83, 84 versus 83, and 85 versus 83. You take all those differences, square them, add them up. You do that for all the 4 groups, all the 4 majors in this case, and your total variability is that 40. The degrees of freedom is 16. That comes from the fact that we had 4 groups of 5, so 4 times 5 is 20 total data points, and 20 minus the 4 groups gives you the 16 degrees of freedom for the error term. Now 40 divided by 16 is 2.5, so then the F stat is 0 divided by 2.5. Okay. Now the p-value turns out to be 1. In other words, this is the smallest F can ever get. So the MS major just says there's no variability in the sample means, and the MS error says there's some variability due to random chance. And notice that the error variability, that random component, is huge compared to the differences between the majors. So in this case, this doesn't convince us at all that there are differences in the population means. So we would come back and say, you know, at whatever our alpha level is, there's basically no evidence, or little to no evidence, that any of the majors differ in mean course grades given this data. Now in the second one, this is where it was obvious, right? Your nursing and middle grades education students had a sample means of 83. The psychology had a sample mean of 93, and biology had a sample mean of 73. And within variability was small. It was the same as what we had in the first example. So that's why the sum of squares is still 40. But the between, right, how much are 83 versus 93 and 83 versus 83 and 83 versus 73 and all those comparisons, how much variation is there in those sample means? Well, that's huge now, right? So the sum of squares is 1,000 divided by the degrees of freedom to get your mean square. That's, 333 1/3. Well, now the mean square is huge. There's lots of variability between the sample means compared to what you see random by chance in the error line. So 333 1/3 divided by 2.5 is 133 1/3. So that's why your F stat is so big now. And notice the p-value is minuscule now. It is basically very close to 0, which means, oh yeah, we're going to reject the idea that all the means are the same, because this data is very convincing that all the population means are not going to be the same. Okay, so there's overwhelming evidence that the majors differ in mean course grades somewhere. Okay, not necessarily all of them differ, but at least 2 of them differ. It's pretty obvious. Now the third output is just where you had examples where the data was all over the place and you couldn't really tell what was happening. So in this case, we just have to run the data because we can't really expect or explain, I should say, where the numbers come from. We don't know what to expect out of this. So the sum of squares and sums of squares were calculated, divided by their degrees of freedom, and you get the mean square, and then you can get the F stat. So 2 1/3 divided by 63.325 is almost 0, right? 0.0368 and so on. So that's very close to 0. Now F scores are ratios of squared values, so it can't be negative. So 0 is the smallest that an F stat can be. So you always look for the area to the right of the F stat if you were doing a curve and everything like we're used to doing. So the p-value turns out to be 0.9902, which means this is right in line with what we would expect to see, or either there's so much variability within each group, any differences between groups is going to be hidden by that. We can't say that it's a major effect in that case. So the chance variability, the 63.325, is huge compared to the variability between the treatments or between the means at 2 1/3. So again, we would say there's little or no evidence that the majors are going to differ in mean course grades based on this. So what you're going to have to be able to do in these exercises as you think about these is define your parameters, right? What are the different population means that you're interested in? What are your hypotheses? The null hypothesis is always that all the population means are the same, they're all equal, and the alternative is always not all the population means are equal, or at least 2 of the population means are different from each other. Your decision rule is your standard form. What's the observed value of the test statistics? You're going to have to read this off of your StatCrunch output at this point. So it would either be given in the homework in an ANOVA table, or you would be given a data set and shown how to run that in StatCrunch. Typically we're just going to assume the method is okay in ANOVA. We don't always go back and check those conditions. What is the p-value? Again, you're going to be given that, or either you have to choose the one that makes sense, right? If F is near 0, you're going to get a big p-value. If F is a lot bigger than 3 or 4 or 5, that's when you're going to get a significant p-value. It's going to be closer to 0. Go ahead and make your decision based on the decision rule just like you did before, and then you'd state your conclusion. Now, when you just do the F test at this point, and all you have is basically what I've given you so far, like the ANOVA table. The only thing you can say is, okay, I reject the null. Yes, there's evidence that not all the population means are equal. Or I fail to reject the null. No, there's not evidence that convinces me that the population means are not all equal, or that the population means at least two of them are different. Okay, so you reject the null. Yes, the means seem to be different somewhere. You fail to reject the null. No, there's not evidence the means seem to be different somewhere. Okay, now the next thing we'll do is build a table of comparisons. This is called a multiple comparison technique, and that's something that you would also be provided. We'll talk a little bit about where that comes from and how you interpret it, but the idea is at this point we're just doing the F test and we're not ready to do the comparisons yet, right? Now when you run the analysis or you have all the output, all of that's going to be presented at one time, but when you're doing the F test, you don't know which means are different or not unless you have the raw data and can eyeball it, like we did in the the second scenario where it was obvious. But if you don't have the data and all you have is the F table, you wouldn't be able to do any comparisons, and you wouldn't be able to tell which means were larger or smaller than others. So we'll save that for another video. So let's look at one more example. So consider an experiment in which a manufacturer needs to decide which of 4 different tread designs to use on a new tire. For each of the tread designs, the stopping distance in feet at 45 miles per hour was recorded for 15 observations. So they put, tread design A on a car, they accelerate to 45 miles per hour, they apply the brakes, and then they see how long it takes to stop. And they repeat that 15 times. Complete a formal analysis and report to the manufacturer which design is best. Okay, so what we're going to do is the F test right now. So we'll assume the method is valid. Notice the measurement that's being made is the stopping distance in feet from a speed of 45 miles per hour, and the factor, or the things that we're comparing, are the different tread designs, and there's 4 levels. So what would be your steps? Well, first let's define our parameters. So the parameters are going to be the mean stopping distances in feet from a speed of 45 miles per hour for all tires with each of the tread designs, and we'll just let the tread designs be called A, B, C, and D. So under the null, we would say the mean stopping distance is equal for all 4 tread designs. So mu sub A equals mu sub B equals mu sub C equals mu sub D. Under the alternative, we're saying at least 2 tread designs differ in mean stopping distances. Okay, so the idea is maybe they're all different, maybe some of them are different and some are not. I don't know. I just know they're not all equal. Your decision rule is sort of your standard form. Reject the null hypothesis. Reject the null hypothesis if the p-value is less than or equal to 0.05. And then we need to look at the StatCrunch output, and we're going to locate the F statistic and the p-value on the next slide. So if you were given the ANOVA table here, what you've got to find is the F statistic. Okay, so remember, that's the ratio of the mean square for treatment over mean square for error. So the 168 number divided by the 22.1 number. And that gives you the 7.602 under F-stat. Now the p-value would be, okay, how much area is to the right of that? Because areas to the right of the F-stat would be even more supportive of the idea that the alternative hypothesis was correct, that there would be even more variability in the treatment, so your mean square number would be bigger. And the p-value is 2 in 10,000, right? So 0.0002. So the p-value is less than, a standard 0.05 level of significance, so my decision would be to reject the null hypothesis. And then the next step is, okay, well, let's write our summary sentence. So in summary, I would say using a 5% level of significance, there is enough evidence to conclude that the mean stopping distance from 45 miles per hour among all tires is different between at least 2 of the 4 different tread designs. Now, what should we do next? What we would want to do now is say, oh, well, let's go look and compare. Let's go think about, okay, what about tread design A versus B, and A versus C, and A versus D, and all those pairs we would compare to at a time and say, yes, I think this one has a larger mean than this other one, or no, I don't think they're significantly different. That is what's called the multiple comparison procedure, and that's what we would do next.